Welcome back, Math 170. We are looking at the fundamental theorem of calculus. For this section, arguably another important rule that we will utilize quite a bit throughout our calculus series. The first part, though, it's not quite as popular because we don't utilize it as much, but it is still very important. We do see it pop up at random times. So I'll show you how it works. And then we'll go with the second part, which you'll like a lot better in terms of it's going to be very helpful with the problems we were approaching in 4.2. So we'll get at it. We're going to look first. They define the criteria of when we can utilize the part one of the fundamental theorem of calculus. Ideally, f is continuous on a closed interval AB, and they are defining a function, another function, g of x, as the integral from a to x of the function of t with respect to t. So kind of want to point this out a little bit. You'll see why in a second, but just a little bit of a note is that the input is x, always. And when you see t in the problem, so here I'll highlight the x so you can kind of see. That's your function evaluated at x, g of x. T is referred to as the dummy variable. It's kind of an interesting way to talk about it. It doesn't really make a difference until after you integrate. But just in case you ever hear it that way, it's not really a joke. Sounds strange that we use the word dummy in calculus, but hey, it's just kind of a placeholder. That's what I like to say. So it's called a dummy variable. So you'll see that you really don't utilize t, but we'll go from there. So the main idea is that the upper limit of integration, you see that it's a variable this time, and it's in between somewhere in the closed interval AB. It could be A, it could be B. And they're making sure that the function itself, g of x, is continuous as well, and it's differentiable. When you take the derivative of it, you're gonna get the input, or I should say the integrand first. I'll see if I can notate it this way. So just like another note, just in case if you were ever worrying about it, if you're deciding to plug in numbers and you wanted to say g of a, you would be plugging in for x. So remember, instead of x, you would be writing a. And still, f of t is part of the problem, f of t with respect to t. But you already know from some of the properties, if you're taking the integral and then the upper and lower limits of integration are the same, you get 0 back. So kind of some things to apply. And so to help you out, just to kind of identify important parts of when we can do this, for the most part, you kind of probably figured out when you took antiderivatives, there is a relationship between an antiderivative and integral. We'll see this a little later in part 2. But as you're taking the derivative of an integral, see if I can mark this off, derivative of an integral, I would like to point out that the upper limit of integration, let's see if I can mark that a little bit better for you. So note, upper limit is x. It's a variable. And also I want to point out that the lower limit is a constant. That's going to be important when we utilize this. So as long as you're kind of recognizing the pattern, we'll see. But they're pretty much saying if you are integrating a function and then you differentiate the result, you get the original function back. So it's kind of undoing what the integral was originally doing. So just so that we can see it, let's see if I can help Just kind of some English to help us really understand what this math notation is. So if a function is integrated, and then the result is differentiated, we get the original function back. So let's see if I can recall what we were doing when we were integrating in the first place. So let's look at this. Recall. We talked about the analogy of a trash collector. Okay, so if I have g prime x, which by the way, it's going to be equal to the function after we take the derivative of the integral. The integral of a derivative spits us back the original function to begin with. G is considered the trash collector. That's our analogy. Maybe there's a better one, but for now it works for us. G increases our collects if f is greater than 0, and G decreases or dumps if f is less than 0. We talk about increasing and decreasing. We kind of pull that into the picture again. So just so that we can kind of see, let me draw a nice little function one more time. A little curvy there. We have a function f. And we're looking at the upper and lower limits of integration from a to b. So I can see if I can go from here. And you could kind of see, well, when the function is above the x-axis, we see two parts. That's letting us know that g is increasing for those two pieces. And then also when the function is below the x-axis, we've got g decreasing. So kind of we are relating this back to a function versus derivative. What's actually going on with the function when you are looking at the graph of the derivative. So kind of play with that. Relook at it in a slightly different way. So we're going to be looking at finding the derivative of an integral in a sense. So when I look at these problems, there's two things I always ask. So always ask yourself, here we go, spell that right, hold on. Here we go, so always ask yourself, does the integral look like the one that we just looked at? So does integral look like the one in our fundamental theorem of calculus part 1, by the way? And what I mean by that, there's two things. Is the upper limit x the variable, and is the lower limit a constant? So if that is the case, it's kind of quicker. So let's look at part A, part B, so we can determine this. And so again, what they're trying to say is, as long as the upper and lower limits match this idea, upper limit x, lower limit constant, when you end up taking the integral of a function, you just grab the function, the integrand first, and then don't worry about the t, you just call it in terms of x because you are inputting that into f of t. So looking at part A, just kind of little note to self, is the upper limit x? Check. Is the lower limit a constant? Check. So if that is the case, when you want to take this derivative, we can say that g prime x, you just pull out the integrand, the function on the inside, but you're going to use the x variable, not t. So it's kind of as nice as that. Kind of a derivative kind of undoes an integral in some sense. And it doesn't really matter how complicated the integrand is. So you kind of notice it looks a little intimidating, but as long as you're checking, again, check the upper limit. Is it x? Yes. Is it a constant? And the lower limit of integration? Yes. So when you take the derivative, that's h prime x, then all we do is we take the function in the integram, but we incorporate x instead of t. That's why they call t the dummy variable. So that is the fundamental theorem of calculus part 1. I want to look at a couple more just to make sure, so that you kind of see that it doesn't always end up being that pretty. Part A, part B are quite nice. But let's look at part A in example 2. And so this is where I kind of look at a little bit of noticing that the upper limit here is not x. Here, the lower limit is not a constant. But I do remember there is a couple properties or some property that allows us to switch those upper and lower limits so that we can put it in the form that we're interested in. So this is where we're going to use the properties to rewrite if possible. So we're going to use integral properties. If we can invoke them, let's do it. Let's see if we can rewrite. And we do have that property that allows us to switch the upper and lower limits. What happens when you do switch the upper and lower limits, it ends up changing the sign of the integral. But what happens now is we can now put the constant. We can put the constant as the lower limit, x as the upper limit. And it hasn't really changed the integrand at all. So we still have 17 minus 5 to the 18 with respect to t. And now that it's in the format, again, upper limit x, check. Lower limit constant, check. Now when we want to take the derivative, so now we take the derivative. Now we can say f prime of x gives us, now keep in mind, what we're looking at is you are trying to deal with, I'll try to color code it just a little bit, the actual integram. So remember, if you take the derivative of a constant times something, the constant is always pulled out first, so that's where the negative sign's coming from. And then the derivative of this integral in this format, all we do is take the inside. So that's 7. Instead of t, we're going to write x. 7x minus 5 to the 18. And the fundamental theorem of calculus part 1 allows us to finish off that problem. So now we're done. So kind of keep in mind, whenever you're not in the format that you want to be in, sometimes the properties help, and then I have a couple more to play with to give you an idea of what happens when it gets a little bit rougher. For instance, looking at part B, what I kind of noticed for myself is the lower limit constant. Yes, so that's good. But here, the upper limit, it's a little bit more complicated than just an x. Okay, so here's the issue. That's kind of going to remind us of something. Whenever it's a little bit more complicated, so it's not just an x, what you can do is you can replace it with another dummy variable in a sense. So I want it to look like just a single variable. So let's kind of show you. if I can do that for you, number 1. We still have 0 here. And I'm going to utilize t as in a sense, a dummy variable. So I want it to be, let's replace it with a t. Okay, let's replace x squared with t. So what does that really mean? You're letting t equal x squared. Okay, so we're going to replace that with t. So what ends up happening? When you plug it in, okay, we still have this cosine. Nothing was changing there. But the issue is what's happening with this t now that you've done, let's highlight that so you can see it. What's happening to this t when you replace it, replace the x squared with it? T itself, see if I can highlight, t is no longer just t, it's actually a function of x. So I'm kind of highlight that just so that we see it. And I'm going to notate it so that you can understand what I'm trying to get at. Technically, t is a function of x, since we kind of use this quick substitution in a sense. So t's there, we still have the square, and we're still taking it with respect to t. So this allows our lower limit to be a constant, our upper limit to just be a single variable, no exponents, no coefficients other than 1s. So by the fundamental theorem of calculus part 1, we can say that g prime x, remember we're taking the derivative of this original function, is equal to the integrand. So if I can kind of help you out with this. So let me write this out for you. So we have our integrand. So it's cosine of, now t was not a t, it's x squared. Okay, so let's see if I can replace it so I can show you that we ended up having it's x squared. So it's the integrand, it's really what t is. We're using the same outline of the function. But the only issue is that since t was not just t or a function, it's actually a function of x, we have got to use the chain rule on this. And so that's kind of my key, is anytime you notice something's more complicated than just an x, the chain rule comes into play. So what we end up saying is we attach on a little link. That is the 2x, that is the derivative of the upper limit. So I'll try to simplify this a little bit just so that we can see. Let me clean it up so we can have the actual answer. What do we have? The 2x, usually it's better in front, and then we have cosine of x squared is cosine x to the 4th. And so that is our final answer for that. So what I end up doing, I don't take so much time to kind of show this all the time, because it tends to kind of confuses us in a way. I just want to make sure when I'm going through these is that whenever I am utilizing the fundamental theorem of calculus, but it was in a, like the limit of integration, the upper limit's more complicated than just an x, what you see me doing is I'll take the integrands all the same, but I have to understand what I plugged in. So let's play with it one more time. Keep in mind, when you use this on this type of function, I'll try to re-highlight. Taking the derivative of an integral allows us to take the integrand as part of our answer, but the integrand is evaluated at whatever this complicated part was, the upper limit of x, and that's what my orange is looking for. So instead of t squared, it ends up being x squared. But then we also have to remember to take the derivative of the upper limit. So that's where this is coming from. So you have to kind of sit there and really look at it and just be careful. Sometimes it takes a little while to sink in. So I'm gonna do a couple more, and then of course, practicing it is gonna be a lot of more benefit to you than just watching us go through the video. So as you can see with part C, h of x, you're kind of noticing when you're playing around, what's the caution here? The upper limit is a constant, and the lower limit is more complicated than just an x. And our whole goal, anytime you're using this part 1 of the fundamental theorem of calculus, get a constant as the lower limit and just a nice x or a single variable as the upper limit. So if we do that, before we can even do that, we're going to use the properties to switch it off. So I'll kind of look at this and say, well, if I use the properties, I can switch the places of the upper and lower limits. So if that is the case, I now have a 1 as the lower limit and a sine of x as the upper limit. I have not changed anything else. The integrand is still there. So it's the cube root of t to the 4th plus t squared plus 1 with respect to t. So now as you're looking at this, first thing you're kind of saying is, yes, I got a constant in the lower limit, but my issue is that this is more complicated than just an x. And so what you're trying to say is you're going to let t, a single variable, equal your upper limit of integration. So if that is the case, then what happens is we can rewrite this. Probably need a little bit more room. And maybe I'll wait on this one. Let me kind of go through one more time. Let me highlight if it is possible. If your t is equal to sine of x, keep in mind when you use the fundamental theorem of calculus, let's try this. We have h prime x, right? Okay, so the negative sign is already coming from the fact that we switch the limits of integrand. It is true, you can pull out the integrand itself, but if you let t equal sine x, what you're doing is you're replacing all of those t's with sine x's. So see if I can write this. You're evaluating the function at sine x. Right, Laika? Yeah, thought so. Okay, so we have sine x to the 4th. That was the t to the 4th. See if I can highlight that. We have plus. Instead of t squared, it's sine of x squared. I'll highlight that for you. And we still have a 1 that didn't really change anything. But once you use the fundamental theorem of calculus, all you're doing is replacing the t's with whatever was more complicated in the upper limit. You have to remember the chain rule. You cannot forget this. So this is all multiplied by cosine x, and that is the chain, and it was the derivative of the upper limit. So if you want to rewrite it, you can. Sometimes people will prefer to say, okay, well, it's better to put the cosine x in front of the radical. And if you have sine of x to the 4th, sometimes people will say, why don't you write it in the prettier version, like sine square x and a plus 1. But for the most part, it does its purpose just nicely. So again, moral of the story, you can take the integrand itself, that is the derivative, but anytime you see a t, replace it with whatever the complication was, the sine of x, and then don't forget to attach on the link for the chain, derivative of the upper limit. So have fun with that. We do one more, and then I set you off to practice with your WebAssign. So here at part D, see if I can open that up a little bit more for you all. I would like to point out, unfortunately, neither of the limits is a constant. We were hoping we would at least get one of the constants from this. But we have done this before. We can utilize the properties of integration. We can actually utilize this and take the scenic route. So this is where we use properties of integrals to take that coveted scenic route. And what that means for me is to introduce that constant. So most of the time people are really excited to introduce constants, but the only issue I have to be careful with, I can introduce any constant I want except for 0. So a little caution, little note in our case. We're not allowed to use 0 in this particular function because it makes the integrand undefined. So if you have this, what do you have, 1 over 0 if you were to use that, and it's undefined. So sometimes you just have to be really careful, particularly with some of the rational functions and sometimes some of the radicals, but we'll go from there. So you just kind of think, well, what's the next best number to 0? At least kind of nice to us. I prefer 1. That's kind of nice. So again, when you take the scenic route, let's kind of draw a quick picture here. It had started off as x squared x to the 3rd. Remember, when you take the scenic route, the constant itself is allowed to be outside anywhere. It could be anywhere outside the upper and lower limit. So I'll just throw it out here. Now, if that is the case, when we rewrite it, we have not taken the derivative quite yet. I still have f of x. I'm going to start off with the lower limit of integration. So again, the lower limit of integration in our case was x squared. But now I can pull in the scenic root. There's that 1. So I still have 1 over t with respect to t, no problem. And what I can do here is add it. Same idea. We are going to preserve the upper limit, which was x cubed. And now we have the constant that we introduced. That's the lower limit. So just kind of make sure you set that up before you try anything. No mental math here. Just make sure you're clear about what you're doing. They're going from x squared to 1 and then 1 to x cubed. Now, once we have this, you kind of have to think, okay, well, I'm almost there. I got constants involved with my upper and lower limits. It looks like this first integral is going to be the issue. So here, we can utilize the property. We still haven't taken the derivative yet. But what I will do is I will utilize the property to be able to switch the order of the integrands. So x squared is on top, 1's on the bottom now, but remember I pulled out a negative sign to change the sign of it. I still have 1 over t dt. And I'm good to go on the second integral because it's already got a constant. Feeling pretty good about that. Now we're almost there. Now, and maybe I'll take a little page from there. So now you can actually calculate the derivative because we have the constants in the denominator, and we do have some variables in the numerator. The other issue, the only thing is that you have to be careful about is it's a little more complicated than x. So this is, in both cases, we're going to have to use the chain rule. So if you take the derivative, we're going to preserve the negative sign in the front, no problem there. Now remember, you are taking the format of the integrand. So the integrand is 1 over t. But instead of t, you're replacing the t with an x squared. That's kind of the issue with whenever you're more complicated than just an x. The other thing you have to worry about is you are using the chain. So the link that would go on is the derivative of the upper limit. So we're going to multiply a 2x to this. And by the way, that's the chain. And it's the derivative of the x squared upper limit. Same idea for the other one. There's still a plus sign. Again, you're going to utilize the integrand, which is 1 over t. But instead of t, we are going to plug in the upper limit, which is x cubed. Now, when you do that, the extra piece you have to attach on is the derivative of the upper limit. So in our case, derivative of x cubed, it's the chain link, derivative of x cubed is 3x squared. Now, if you want to make it prettier, that's ideal. Like sometimes WebAssign gets pretty picky. When you have, let's just kind of clean it up again. What do we have? Negative 2x over x squared plus 3x squared over x cubed. And yeah, that's prettier, but not prettiest. One more thing, just kind of simplify your dividing with the same base. You can play with the exponents. So what do we really have is negative 2 over x. And then 3x squared over x cubed is plus 3 over x. And now those happen to be like terms. So guess what? Combine them. We end up getting 1 over x. Interesting. So please utilize this. Practice it a lot more. Sometimes just watching it the first time, it doesn't quite sink in. But all I will caution you is whenever you're utilizing this first part of the fundamental theorem of calculus, always make sure upper limit has to be a single variable, the lower limit has to be a constant. And if not, you have to play around with properties to help you rewrite. Or if it's more complicated than just a nice x, then you can still utilize it, but you have to attach on the derivative of that more complicated piece to the end of your function. So hopefully this helps a little bit. Keep practicing with the WebAssign, and I think you'll have it by then. So now, this is what we've all been waiting for, really. If I had music or something, I would play it to like sound trumpets, but this is a really valuable part of our calculus. We actually will utilize this a lot more in Calc 2 and then the rest of this semester. But this is a very, very powerful idea that as long as your function is continuous on the closed interval, it finally relates the integral to an antiderivative. And so you're kind of wondering, wow, well, that's why we pushed chapter 3.9 or section 3.9 a little bit closer to chapter 4. It makes more sense. So what they're trying to tell us, if you are playing with evaluating the integral of a function, you basically look at the antiderivative. I was going to highlight that in yellow. The antiderivative of the function itself. And what happens is if you find the antiderivative formula, all you have to do is plug in the upper and lower limits to that antiderivative formula and subtract them, and you will have the actual value of the integral. And I know maybe we're not live, so I guess you're not as excited, but this is a really, really valuable tool for us now. It basically allows us not to have to keep calculating everything with limits and summations. And you notice when we were playing with that very last one, well, I asked you guys to do that on your own. It got pretty complicated with that summation. So this is going to be really, really nice for us, and it's going to allow us kind of more of a streamlined process. So just another version, if you want to look at the fundamental theorem of calculus part 2, you want to look at another version, it kind of gives you an ideal that if I can play with this, so I look at the left-hand side, this is like saying the definite integral. Remember, definite just means that they gave you upper and lower limits of integration. The definite integral of a derivative over a closed interval is equal to the net change of the function over the integral. So in other words, what was the function before you took the derivative, i.e., who was the antiderivative? So there's a couple ways to look at it. I really like to perform antiderivative first, and then we go from there. So let's see if we can go through a couple of these and then really try to see like the difference between some of the techniques. As you kind of were playing around with x cubed last section, we now have a faster way to get through these. So if I'm going to evaluate, and notice it didn't really tell me what technique to use. So yeah, you could use the limit definition if that was something that you were really keen on. But now that we have this fundamental theorem of calculus part 2, just kind of keep in mind that we're looking at the antiderivative. So let's see if I can write this out. We're going to look at what was the function before we took the derivative. We call this antiderivative evaluated at 2 minus antiderivative evaluated at, not 3, at 0. Okay, remember where I'm getting these values from? The upper and lower limits of integration. So a lot of times what people like to do, there's more than one way. I'll show you kind of the notation. A lot of times when we first start off, we're saying f of x was equal to x cubed. Our antiderivative, if you remember, if you have a power function, you add on 1 to the power and divide by the same thing. And so some of you already noticed a pattern in 3.9 that it's like x to the 4 over 4. Well, what does that tell us to do? What we end up doing is we're saying, okay, we're going to evaluate that antiderivative formula based on the upper and lower limits of integration. And so you kind of see, okay, do a little bit of math. 2 to the 4th is what, 16 over 4, and 0 to the 4th is still 0. Don't have to worry about that term. And so 16 over 4 just gives us 4 minus 0 over 4. And so that is the quicker way to evaluate integrals. And actually, I can even make this a lot quicker. I think one of my preferred notation, another version of notation, alternate, and it tends to be a little more popular when you have more complications. Again, we're looking at the integral from 0 to 2 of x cubed with respect to x. What you can do is think about what is the antiderivative of the inside. And so that is where we're getting x to the 4th over 4. And now what we end up notating is it's not just x to the 4th over 4, it's evaluated from x equals 0 to x equals 2. And a lot of times people won't even write that. What they will do is they will use a new notation where you already know you're plugging in x's, so they will just say 0 to 2. So I kind of prefer, we start training ourselves. This is kind of nicer to show. And then now you can show, oh yeah, well that's the same thing as saying 2 to the 4th over 4 minus 0 to the 4th over 4. And yeah, we're still getting the same value. Still number 4, no matter what. So kind of some new things to play with, but you will get used to them, I promise. And we will be utilizing integration a lot more in calculus 2. So we're gonna, right now we're just dealing with some of the nice power functions and some of the nice versions of trig functions. And then Calc 2 will give you a lot more techniques to play with. We still utilize this fundamental theorem of calculus, though, a lot. So let's try this with part B. I kind of keep in mind with part B, I noticed when we were doing these with limits, definitions, we were really wanting to have a lower limit be 0 because it makes everything easier when you plug everything in. We tried something similar in 4.2. Is it 4.2? Yes. And we realized that, yeah, you can split this integral up into 2 separate integrals, but it ended up being quite complicated still. Still had some issues. So now this fundamental theorem of calculus, what it allows us to do is it doesn't care who the upper and lower limits are. It still allows us to say, hey, that's the same thing as saying the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And so if you remember, in both cases, the antiderivative was x to the 4th over 4. So that's where we were getting 2 to the 4th over 4 minus negative 1 to the 4th over 4. And I'll show you just so you see this. And so now we just say, okay, well, that's what? 2 to the 4th over 4. I think we found that already. That was 4. 1 to the 4th over 4 is 1 over 4. And then we just do a little bit of fraction math, and I think we get 3 3/4. Or if you guys like improper fraction, what is that? 15. 3 times 4 is 12 plus 3, 15 over 4. Sometimes you'll see that as a preferred mode of entering your answers. Either one is fine, though. You should be good either way. So you'll kind of say, like, I'm pretty good at plugging in things to formulas, and that's true. That's why we love this fundamental theorem of calculus part 2. You want to make it a little alternate, kind of get used to this a little bit. One more time, kind of re-demonstrating the way I see it is whenever I'm looking at this, first thing I will do is say, what's the antiderivative of this power function? And so that is for sure, it's x to the 4th over 4. And then you're going to show who you're evaluating it on. Who's the lower limit? X equals -1, upper limit, x equals 2. And so now, without going through everything, you can kind of see, okay, that means all I do is plug in everyone, 2 to the 4th over 4 minus -1 to the 4th over 4, and we still get the same answer. Was it 15 over 4 or 3 3/4? So sometimes that helps you see it a little bit better without having to do all this extra work on the side. You can kind of incorporate it in your problem. So once you get kind of used to that, this is kind of a good problem to go over where we ask you a few different ways to evaluate integrals now, so you can kind of see the difference. So it's like a good idea to test questions like you'd like to do this. They like to compare all 3 methods. And ideally, these are all supposed to be the same. So for part A, they want us to approximate the integral using the midpoint rule with n equals 4. So you kind of have to think about what is that really meaning. What I'll probably do is show this off to the side is, this was like when we're using what left limit and right limit, and midpoint is the midpoint. So first thing I'll do is calculate my delta x. And always our delta x is the b minus a over n. Well, in our case, it's 2 minus 0 over n, or 2 over n. And now, if n is equal to 4, what is that? 2 over 4, which is 1/2. So we have to have a clear idea of who delta x is. So the second thing I'll do for myself, whenever I'm using like left side, right side, midpoint rules, I'll kind of draw my left and right endpoints. So you'll kind of see, okay, I have a 0 to start with, and I'm using my idea of delta x. So delta x, I'm adding on 1/2. So I can figure out what's the points as I go. So I should see 1/2 right here. If you add on another 1/2, that's 1. When I add on another 1/2, that's 3/2 or 1.5. And when you add on another 1/2, that should be our right endpoint 2. So I'm just getting a good idea of what my interval looks like, of what I'm trying to approximate. The next thing is I have to understand, am I choosing left point or right, left side or right side? They were clear and they want us to use midpoint. So this is where, instead of calling everyone x1, x2, they chose us to look at who's the midpoint of each of these intervals. So there's 4 rectangles eventually, and they call this x sub 1 star, x sub 2 star, x sub 3 star, and finally x sub 4 star. So what you can do is you can eye this if you need to, but just in case you were wondering, what I'm trying to get at is my x sub 1 star. It's in between 0 and 1/2. Well, it's the average of the two. That's what midpoints do. 0 plus 1/2 divided by 2. But we don't necessarily have to do the math if we understand fractions. It's 1/4. You want to try that again, x sub 2 star. What is that? 1/2 plus 1. Divide by 2. So what should we get? 1/2 plus 1 divided by 2. That's about 3/4. But we kind of knew that based on how we set up the problem. So if you kind of draw a picture of the number line, you don't necessarily have to do all this math. So similarly, if I'm going through this 1 plus 3/2, I can kind of now count. And I don't know, feel free to play, but I can now kind of say if everything has a denominator of 4, what is it? 1 is 4 over 4. So this next midpoint, x3, should be 5 over 4. 3/2 is 6 over 4. So the next midpoint should be 7 over 4. So I'm doing a little counting and I kind of double check that I'm ending with 8 over 4, which is equal to 2. Feel free, if you have a better time showing the averages, that's totally okay too. But now, once you kind of understand what these are, when you approximate the integral, so now we're looking at the integral from 0 to 2 of our f of x dx. Remember with the midpoint rule, what they would tell us to do is say that's equal to delta x times your function evaluated at all these points. So I'll kind of give you the generic version. And if we were to factor out the delta x, that was like f of, what is it, x sub 1 star plus f of x sub 2 star plus f of x sub 3 star plus f of x sub 4 star. That's our midpoint rule. Now, if you want to make this generic to our formula, and let me be a little more precise here. Technically, this is approximation, so I'll use the approximate instead of equal. What were we trying to find? The integral from 0 to 2 of x squared dx. So now we have the approximation. Who was our delta x? That was 1/2. And now if we're looking at this, we're looking at the function evaluated at all our x1, x2, x3, x4 stars. So I kind of go back and say, what were those values? It was 1/4, 3/4, 5/4, and 7/4. 1/4, 3/4, 5/4, and 7/4. And now you're knowing, well, who was f of x? Well, f of x is the integrand. So that ends up being 1/2. F of 1/4, what do we have? 1/4 squared plus 3/4 squared plus 5/4 squared plus 7/4 squared. So we end up saying that's 1/2. We do a little bit of fraction math. What do we have? 1/16 plus 3/4 squared is 9/16. 5/4, 25/16. 7/4, 49/16. And if you want to, this is where I would probably, oh, they're all common denominators already. But shouldn't we get something like 1 plus 9 plus 25 plus 49? We should get 84. So half of 84/16. Or if we want to simplify it a little bit, we should get 21/8. And that is approximation. So if you, I prefer to keep it exact, but it is an approximation. If you would like to kind of see how this compares to what we end up getting really, we can then approximate to see what the value is. It's 2 point something or whatever. So again, that's a little bit of a review from 4.1. Brings it back into the front of our minds again. That's using the midpoint rule. Now what they want to do is say, let's look at the later part of 4.1. And we kind of said there's a way to actually get an exact value for this, but we have to use the limit definition. So again, the directions are very important. If you don't utilize them and you end up finding the answer, you may not get full credit. So we want to kind of show if we are doing the limit definition. I believe we did this before, but let's go with it. Limit definition, I'll write it out. I want to look at it in terms of, let's write it out. So the integral should equal the limit as n approaches infinity of the summation I equals 1 to n of f of x of I times delta x. And so then that is going to involve us finding who's delta x. Well, that's b minus a over n. So in our case, it's 2 over n. Then we have to figure out who's x of I. That is a plus I delta x. So I'll just kind of write that in. Whose delta x is 2 over n. We're getting really good at it. We don't have to necessarily write out the formula each time. So I should have 2i over n. I can look at now evaluating the function at the x of I just found. And so our function is x squared. So that's 2i over n squared. Let me simplify it a little bit. What is that? 4i squared over n squared. Then we kind of say we're still looking for this part. F of x of I times delta x. So f of x of I times delta x is 4i squared over n squared multiplied by 2 over n. So that should finally give us 8i squared over n cubed. So now we're ready to plug that into our limit definition. So kind of the preliminary work. So if we do this, we have the limit as n approaches infinity, summation I equals 1 to n. And now we can directly say of 8i squared over n cubed. So it's a little prettier now. Then what we end up doing for ourselves, we can factor out items in front of the summation that do not involve I. So this is where we see ourselves factoring out 8 over n cubed. But we still have the summation of I equals 1 to n of I squared. And so that piece right there, we have the nice formula for that. Let me rewrite everything. Limit as n approaches infinity, 8 over n cubed. This is going to leave us with, what is it, n times n plus 1 times 2n plus 1 over 6. And now you kind of clean up the inside to help out. You can either do Bill Gates' simultaneously, or you can clean it up if that's something that you want to make it visible for yourselves. So what I might do is kind of limit as n approaches infinity. If you feel like reducing, what do we have? 3 goes into 6, excuse me, 2 goes into 6 3 times, 2 goes into 8 4 times. So I'll have this 4 over 3. I could also reduce out one of the n's, n, and make it an n square, I suppose. Yeah, might as well. That's n square. And then also, if you want to invoke Bill Gates, then you can take the leading term of everyone. So I still have an n and a 2n. So what does that leave us with? You could kind of see where the limits divide out. The n's completely divide out. We get 8/3. And actually, limit of a constant is just 8/3. We have the exact value of the integral. So now if you're interested, you could kind of see, well, how close was our midpoint approximation? So if you're interested, you can say, what is that equal to? We can, let me see, I'll punch it in. You don't have to see this, but I know you know how to do this. 21 divided by 8 gave us 2.625, and 8/3 is 2.6, 2.66, and so on. So, I mean, it's pretty close. Even with just 4 rectangles, that kind of helped us. If you wanted to break it up into 8 rectangles or 16 or anything larger, we probably get pretty close. It's already pretty close, but we have the exact value right here. That's what we're interested in when we do the limit definition. And now, my friends, you get to see when we're actually doing this with the fundamental theorem of calculus, how fast and how powerful it really is. Remember, we're looking at the integral from 0 to 2 of x squared with respect to x. Well, if we take the antiderivative of the inside, that becomes x cubed over 3. And we evaluated at the endpoints from 0 to 2. Well, now we end up getting, what do we have? 2 cubed over 3 minus 0 cubed over 3. What happens to those zeros? 0. 2 cubed over 3 is 8 over 3. And look at this. Look how fast we found it. And so that's the power of this fundamental theorem of calculus. If we can utilize this, you can find these integrals quite fast, as long as you have nice formulas for them. They could get quite complicated later, but we kind of work with some of our functions as we know them now. So the only thing that's stopping us from using fundamental theorem calculus all the time is that the directions. So just kind of be careful as you're going through tests or quizzes. Make sure you're utilizing the correct directions. It is important to do both. And sometimes you guys kind of wonder, like, why am I using limit definition when it's so much nicer to use fundamental theorem of calculus? Part of this practice with summation notation ends up prepping us for a lot of the sequences and series we see in Calc 2. So it kind of gets you thinking a little bit more once we approach that a little bit later. So not a bad idea to practice both. And of course, for this class, we do need to have both down. So that, having said all that, I would like to give you ideas that we're going to have these common antiderivatives or integral formulas that we end up using a lot. So might as well kind of introduce them now. So I'll kind of help you out. We already kind of know item number 1. It's really the most useful. This semester is like the one we always use is anytime you're taking the integral of a power, then that's equal to, what do? Add 1 to the power and divide by the same thing, as long as our n is not equal to -1. This semester, we're not going to be able to integrate x to the -1. We're going to save that for Calc 2. So I'll give you a little note. So integral of, what is it, x to the -1 with respect to x is the same thing as integral 1 over x with respect to x. We're going to save that for Calculus 2. That's a transcendental function, so we'll go from there. Now, notice, I'm going to be clear on this. It's going to matter a lot more for the next section. But when you do not see upper and lower limits of integration on the integral symbol, it's going to make sense a little bit more later. We don't tend to use it this way, but I might as well get you in the mood now. When you're done taking the antiderivative, you always have to add on a c to stand for plus a constant. Remember how we did that with the family of antiderivatives? It still holds in place. And that's like the #1 thing we forget in Calculus 1, Calculus 2 is that extra c at the end. So definitely we're going to see this in 4.4 where you need to attach that. It's worth points. Please do so at all times unless you see actual upper and lower limits of integration. You'll notice that the other ones that we've been dealing with, item number 2, you've seen it before as well. It's a constant times, it's actually the integral of a constant. And all it does is add 1 onto the power. It's kind of an application of item number 1, but a lot of times what we just say is, hey, we attach the variable of integration to that constant, and don't forget our plus c. So integral of a constant is constant times the variable plus c. And now, this is where you end up seeing a lot of these. I'll give you a few more, but common ones like sine. You want to say, well, what was the derivative? The derivative of what is sine? And so we can kind of play with kind of what I told you earlier is you have the function itself, you have the derivative. So you guys can play with some of these. Derivative of sine is cosine x. Derivative of cosine is negative sine x. Derivative of tangent is secant square x. Well, if you're trying to get a sine, it has to be that the function before had to be a cosine, but remember, we have an issue with a negative. So a popular function to integrate is sine, but that would leave us with negative cosine x. Let's make that a little nicer for you. And then don't forget, if you don't have upper and lower limits, we are adding on that c, to be seen in the next section. Bless you. So we kind of can now look at, well, derivative of what is cosine? Oh, right away. Sine of x, bless you. Someone's allergic to calculus, huh? Okay, you just don't like integration, I get it. So we have sine of x plus c. And now you could kind of say like, secant square x, that's common. The derivative of what is secant square x? It's tangent x. And don't forget we're adding the c because we don't have upper and lower limit. And you're kind of noticing, oh, well, what made a secant x tangent x? Trying to think, well, you can now play with, we're missing some trig functions in our chart. So what are we taking? The derivative of secant x is secant x tangent x. So that's where we're getting the formula, secant x plus c. And what other ones are we missing? We go back and say, well, I think we're missing the cosecant one. That's something that comes into play. So let's see, what's the derivative of cosecant? That's negative cosecant x cotangent x. So if we were to kind of say, what's that? we're going backwards. So the integral of, I could play two ways. If you want to say what's the integral of cosecant x cotangent x, we have to be careful because yes, we do know it's cosecant, but the original one had a negative, so that's where we're having this negative come from. And you'll kind of see negatives appear and disappear as you go. Just kind of pay attention to maybe having a chart on the side of your trig functions and their derivatives, and it really helps you see when you need to replace negative sign or not. Similarly, the other one I'm missing, I think I'm missing a cotangent. So derivative of cotangent x is, what is it, negative cosecant square x. So just to kind of show you, if that was something you saw, let's say you saw this, negative cosecant square x. Well, now you don't have to replace the sign because it's already the derivative of cotangent is there. So you just have cotangent x again plus c. But like if we're kind of going without signs, if you had something like the integral of cosecant square x, notice that we don't see the sign, so you have to kind of throw that back in. So they kind of are related. You just kind of maybe have to be really good at identifying your trig functions so that you can integrate them when they come up. So really, really important, not just now, but Calc 2 utilizes a lot of trigs. So like I said, when you're first starting, write a nice chart for yourself so you can start recognizing them. And after you do a lot of them, you're going to find that they come natural as well. Let's do a few examples, kind of give you some more experience, and then I'll show you kind of a shortcut on your TI for some of these. It's kind of nice. Let's look at example 5a. I'm looking at the integral of x squared dx. And again, this time around, notice the upper and lower limits of integration. They're not just zero. So I'm just going to apply the formula. That's the fundamental theorem of calculus. We're going to just look at the antiderivative. And when you first start off, you know, maybe it is important for you to show that you're adding 1 and dividing by the same thing, but don't forget that you're writing what you're evaluating. These already have upper and lower limits, no need for the c. So what does that look like? X cubed over 3. And still evaluating from 1 to 4. And then when we go through this, what are we plugging in? The upper limit minus the lower limit. So upper limit is 4. So it's always upper limit first. And then lower limit is 1. So then it becomes a nice fraction. If you're interested, if you notice, the 1/3 is technically a constant. If this is something that excites you, you can factor out the 1/3 and just do the math, if that's something that makes it a little easier on your eyes. But in the long run, what 4 cubed is what? 4 times 4 times 4, 64 minus 1. In the long run, you still have to attach the fraction. So we get 63. So that becomes 63 over 3, and we have a nice exact value. So kind of feel free to play around with it. I tend not to factor out the fraction unless I see something kind of disappear right away. So part B, kind of notice radicals. I know they didn't give us a rule for radicals, but before I even deal with radicals, even when we were doing derivatives, we rewrote it. So it's not a bad idea. Take your time, rewrite your radical so that it turns into a power function. So we should have x to the, let's see, if it's cube root of x squared, that should be x to the 2/3 with respect to x, of course. So that's not the integral yet. Now it's time to find the antiderivative. So this is a case where I'll probably utilize that power rule and show my steps. antiderivative takes the 2/3, it adds on the 1. Then it divides it by what you just did with the math. So we still have the 2/3 plus 1. Don't forget, you're still evaluating it from 0 to 4. If you don't write that notation, you are incorrect. So now what we do is we can say, okay, well, we just kind of simplify a little bit of math. 2/3 plus 1 is that 2/3 plus 3/3, which gives us 5/3. And then we still have 5/3 in the denominator. Still evaluated from 0 to 4. And then also you'll start noticing when you integrate functions that have rational exponents, you start seeing a pattern that you're technically just taking this denominator and you are multiplying by the reciprocal when you rewrite everything. So whatever works for you. The more you do, the better you get at it. So now what happens here, I will take the fundamental theorem of calculus. I have the 3/5. If this helps you, the 3/5 is on the outside. We can leave it there if you'd like. But now we're taking fundamental theorem of calculus, and we're just saying that is 4 to the 5/3 minus 0 to the 5/3. And you'll start noticing, oh, when there's a 0 in the lower limit, we don't really need it. It turns into a 0. So now what we're looking at is 3/5. And sometimes, I mean, this is kind of up to you. We're trying to get radicals. If sometimes we end up having to find actual values, and depends on what our calculator is telling us, but we could take this 4 to the 5/3 part off to the side if you go back and say, well, 4 to the 5/3, if it started with radical, maybe they want it to end with a radical. So what is that? A cube root of 4 to the 5th. If that's something interesting, I don't know. And so if we have a cube root of 4 to the 5th, we could kind of say, well, that's the same thing as cube root of 4 cubed times 4 squared. So for sure you can take a 4 out, but then you have the cube root of 4 square. But then you're kind of thinking, wait, 4 square is 16. And I mean, you could take all day on this if you're kind of saying, okay, well, what is 16? 16 is 2 to the 4th, or 2 times 2 times 2 times 2, if that helps. So anytime you see a group of 3 for cube roots, you pull one out, and you're left with cube root of 2 on the inside. So what is that, 8 cube root of 2? So if that's something that you're interested in, depending on what they want in the final answer, this is 3/5 times 8 cube root of 2. So at the end, you'll get your answer. It's a little ugly, but what is that? 24 cube root of 2 over 5. So it's one version if they're looking for exact answer. It kind of depends on what's the preference here. So have fun. So let's see if we can do this. We have another few more to go before we end, just some nice sample ones. Let's play with an integral of a polynomial. So nothing too much different other than the fact that you're using your properties. You're saying, well, I already know integrals of powers and constants, so all I can do with part C, just think about it as the integral of the different. Oops, let's make sure we write with respect to the variable. So we can split up the integral, sums and differences. Integral from 0 to 2 of 5x with respect to x, and integral from 0 to 2 of 7. And if it makes it a little bit nicer, I might as well just say, if I'm using the sign, might as well take the subtraction. If that's something you want to do, great. What I tend to do I'm thinking about it this way. Notation-wise, you might not even see me do the split up of all these. I can usually go straight from here to here and say, well, I'll just integrate each term. So that would be 2x to the third over 3 plus 5x squared over 2 minus 7x, and all of that, want to be precise, all of that is evaluated from 0 to 2. It's another way to look at it. But now when you show this, what I'm kind of seeing is the fact that the lower limit's 2. I don't have to worry about too much plugging in. I just have to worry about the upper limit. So I end up getting, if I'm going to plug this in, 2 times 2 cubed over 3. Let me color code that. Maybe that might be a little more precise for you. So I have the 2/3. That was already there. All I'm doing is plugging in the upper limit, which is a 2. Same thing here. I have the 5/2. All I'm doing is plugging in the upper limit and then subtracting off 7, plugging in the upper limit. Now this, just so that we are clear, this is the first half, fundamental theorem of calculus. The antiderivative plugged in, evaluated at 2. Now, check out what happens when you plug in 0 to every term in this antiderivative. Every term has an x, so all you're getting is you are subtracting off a 0. So you don't necessarily have to write that out if you see it right away. So the math ends up being you just simplifying some of the fraction stuff. So we should have 2 times 2 cubed, what is that, 16 over 3. 5 times 2 squared is 20 over 2. 7 times 2 is 14. We can play with a little bit. 20 over 2 is actually 10. 16 over 3 plus 10 minus 14. And then this is where, don't waste your time, use your TI. Use your fraction key because you're already using your brain for everything else. So 16 over 3 plus 10 minus 14. And then just convert it to fraction. So that gives you 4/3. And if you want to see something pretty cool, show you in a second how the TI can help us verify these definite integrals. Well, let's finish this off a little bit with analytical. I'm going to move things over so I'm clear on this. All I'm going to do is just show the last one and then kind of show you how your TI could help you with some of these to see if you're actually correct. Okay, so last one for this section, and then we'll kind of show you the TI trick, which I really like. Again, this is an integral of a difference. So you can find the antiderivative of each term, just make sure you're adding and subtracting accordingly. So I see the first part for me. I see the integral of 3x squared. So 3 is a constant. The 3 will come out already. If you're taking the integral of x squared, antiderivative is x to the third over 3. Now we could subtract off. I see 2/3 is a constant. I'll leave it. The square root of x, excuse me. Remember the square root of x is x to the 1/2. So this helps me understand that when I take the antiderivative or the integral, I'm saying 1/2 plus 1, and we're dividing by the same thing. So all of this, once I simplify it, remember it's a definite integral. All of this is evaluated from 0 to 4. So I have to kind of write the notation to help me out. Now, lucky for us, 3x cubed over 3, that's just an x cubed. What I might do is just clean up. The 1/2 plus 1 is 3/2. So if you're dividing by 3/2, we'll clean this up a little bit more. I tend to write out a few more steps because there's a lot of chances to make minor mistakes. If you're dividing by 3/2, you're actually multiplying by 2/3. So you should have x to the 3/2 all still evaluated from 0 to 4. Clean it up just a little bit more. X cubed minus 4 over, was it 4 over 9? X to the 3/2 from 0 to 4. And keep in mind, it should be a little bit more precise. All of this technically applies to the upper and lower limits of integration. A lot of times we'll get a little bit lax in our notation the more we go with. Sometimes calculus 2, when I switch back to calc 1, I forget. We should be precise though. So what happens when we evaluate, kind of the same idea, the lower limit was 0 again. So that's nice because you don't have to really spend too much time finding that extra part. So right away, I know when I'm evaluating, I know that I can subtract off a 0. So everything lies in me trying to plug in x equals 4. So that's where the fundamental theorem of calculus comes into play. So now you can kind of simplify. 4 cubed is 64. If you want to play with the 4 to the 3/2, maybe we take that part off to the side again. Sometimes when it's a radical, we can make it much prettier. So if I kind of looked off to the side and said, okay, 4 to the 3/2 is the same thing as square root of 4 cubed. And notice some of the radical rules. Square root of 4 is 2. So if you're taking 2 cubed, you end up getting an actual 8. That's interesting. Radical completely goes away. So we should get 64 minus 32 over 9. And then from there, of course, use your fraction key. So I'm punching it in. I assume you're okay with that. And I'm getting something like 544 over 9. I'm getting the exact value. Again, remember, we had subtracted off 0. That's because the lower limit was 0. Don't get too used to it because sometimes the lower limit changes. So I just want to warn you. So it's just kind of more skills to go over. A lot of people like these sections because it's a lot of procedure. And if you have procedure, a lot of you do quite well. But a lot of it, you do have to be really careful about what you're plugging in. So I really recommend not skipping steps. That's kind of usually everyone's downfall. But one more thing before we end, I wanted to show you some cool things in the TI. Little note to ourselves. And I tend to use this using the TI. I'll probably use it when we have applications of integrals, unless we're told otherwise. But we can check these. We can check our definite integrals with our TI. And there's a couple things, just kind of syntax to help you out. Number one, it's going to have to do with the math key. And we'll show this on screen in a second. So let's write this out. Let's go back. I'll show you and then I'll switch back. So there's my screen. And now what I'm looking at, whenever I want to actually calculate an integral, I can go use the math key. And what you'd be entering is item number 9. It looks like FNINT, so the function integral. And if you have it's a TI-84 plus or higher, it'll automatically give you this nice integral notation where you could enter everything in. So for instance, if I was entering in my part C, the lower limit was 2, not squared, excuse me. Let me go back there. I want to use the arrow key to get to the upper limit, which was So lower limit 0, upper limit 2. And now you could enter in your function. In our case, it's 2x squared. These are kind of nice when there's sums and differences of powers. Don't forget the plus sign. The plus 5. What is it? 5x minus 7. And you always have to tell the calculator what variable are you integrating with respect to. Like I said, it does matter. And again, we chose x. That's usually common. So now my friends, press enter. And you get a decimal. If sometimes it's able to be turned into a fraction, you can change it directly to a fraction. Sometimes it allows you to, and sometimes it doesn't. And check it out. Isn't that what we got? Let's see, refresh my memory. Oh, yes, we did. Look at that. Pretty cool, huh? So it really worked with definite integrals. Just to remind you one more time, if you're kind of taking notes and you missed that, you're going to select item 9. Usually you're using the arrow key, but that's where you're saying function integral. And if the integral shows up on the screen, wonderful. But if you have maybe like a TI-84 or TI-83, if you want like an older syntax, I'll give that to you. The reason why it said F and INT, because usually that's what shows up on your screen. And the syntax, in terms of like what the code is for older operating systems, is that you're going to enter what the function is, your integrand, have a comma. You always tell it with what respect to what variable. That's the x, according to us. And then you always have your upper and lower limits of integration, excuse me. So that would be lower limits A, upper limits B, and then you close the parenthesis. So for instance, if we were to see this on our TI, for our TI-83, this would show up on the home screen. The function that I would show is the 2x squared plus 5x minus 7. Then I would use a comma. Then I would say, well, I typed in x for the variable, so I have to say it's with respect to x. My lower limit, don't forget the comma, my lower limit should have been 0. And my upper limit, there should be a comma though, should have been, I'll double check one more time, I think it's 2. Yeah, should have been 2. And then once you press enter, you will still get the same number. So we got what, 1.333333, and then we use fraction. And it did give us the 4/3. So that's really, really convenient. A lot of times when we're first starting, we always try to show that we're obtaining this from the fundamental theorem of calculus. Sometimes you can't just use your TI. You'll kind of see it doesn't always give you an exact value. So for instance, if we kind of play with, what is it? We wanted to do the integral from 0 to 4. Let's do part D, just so that you see. So that was 3x squared minus 2 square root of x over 3 with respect to x. I'm kind of wondering what our TI gives us for this. What is it supposed to be? We're supposed to get, okay, so it's supposed to be 544 over 9. That's the exact answer from our fundamental theorem. FTC part 2. So let's see what our TI gives us. Let's go back. Have opportunity. So again, one more time, we're going to press the math key. And we're going to go to 9. It's going to pull up the integral, or the syntax we're going to have to type in. And with our function, let's see, upper and lower limits. So my lower limit's 0. My upper limit is 4. 3x squared Now I'm going to subtract off 2 square root of x, and I got to be careful because I don't want to make sure I have the division sign. It's supposed to be outside. So all of that should be divided by 3. And because I only have a monomial in the numerator, I don't necessarily need parentheses, but sometimes if you want to be clear with respect to x, press enter, and we get 60.4444445. Let's see if it goes to a fraction. And it doesn't. But let me go back to the actual answer. Our actual answer from the fundamental theorem of calculus was 544/9. Our TI gave us 60 point, I'll have to recopy it from my screen. 1, 2, 3, 4, 5, 6 fours. And then it had a 0.5 at the end. So we have an approximation. It doesn't convert to a fraction. Well, let's see what 544/9 is. So what's that as a convert to a fraction? Go back one more time, just to make sure. If I said 544 divided by 9, we can see we're pretty close. Not quite. So we're pretty accurate to about 6 decimal places. I'll kind of show you just so that you can kind of notate it on our notes. And so 545, or let's see, our exact 544/9 equals, there was 60 point, there's 444444444, 1, 2, 3, 4, 5, 6, and then there was an extra couple 4s. Not bad. TI is pretty good to about 6 decimals, but we'll know for sure that you didn't convert or you didn't use the fundamental theorem of calculus because you wouldn't have the exact fraction. So kind of, you know, TI is great, but sometimes you don't get to use it, or sometimes it doesn't give you the exact value. This fundamental theorem of calculus is still quite powerful. So please utilize it. And I think if you practice, you're going to have a good time. Get really good at these. We're gonna utilize this when we do indefinite integrals. But if you understand how to take antiderivatives and understand the formulas, you're going to do quite well in the next couple of sections. So I will see you then.